let's take a look at how we can use this idea called the intermediate value theorem to verify a conclusion if we're given some points on a table, which is actually a really popular way for the AP to ask questions about the intermediate value theorem. So let's consider the continuous everywhere function, and we'll call it f of x, with table values listed below. And so we're going to give a little table of values here for the continuous function f of x. So we'll look at values of x, and we'll look at values of f of x. And the values we're going to put on our table is we're going to put the point 2, negative 3. We're going to put the point 4, 1. We'll put the point 6, 4, 8, negative 2, and the point 10, negative 7. So there's some table values for this particular function. And what we want to do is we want to show that f of x is equal to 3 on the closed interval 2 to 10. And that's the interval that we're given right there. So on the closed interval 2 to 10, does f of x equal to 3? Well, the first thing I know that it was given to us when this function was given is that f of x is continuous everywhere and that means that f of x is definitely continuous on the closed interval 2 to 10. That's a true statement. The reason why I use this example, and there is a little bit of a trick, and you do have to kind of see what you're looking for before you take it on. If I look, and I'm trying to show that f of x equals 3, if I look just at the endpoints of this interval from 2 to 10, at f of 2, I'm at negative 3, and we'll just read the function here. I go from negative 3 to 1 to 4 to negative 2 to negative 7. And so, we don't really know what's happening in between, but we have this understanding that we go from negative 3, we rise up to at least 4, and then we fall back down to negative 7. And logically, it makes sense that, yeah, at some point we have to go through 3, especially because the function is continuous. When using the IVT, though, we're actually going to have to look at a different interval because f of 2 is negative 3 and f of 10 is negative 7. 3 is not in between those values. So if I'm trying to have this airtight argument using the intermediate value theorem, I actually cannot use the interval from 2 to 10. Now I can use a smaller interval within that interval, which is what I'm going to have to do, but I can't actually use from 2 to 10 without at least narrowing it down a little bit. So I need to pick function values where 3 is sandwiched in between them. And there's actually multiple correct answers to this, but to me the one that maybe jumps out the page the most is if I look on the interval from 4 to 6, where I go from function values from 1 to 4, I can see that that means that at some point I have to go through 3. You could do this with 2 to 6. You could also do this with 6 to 8, because as I go back down, I go through positive 3 again. And I could also do it from 6 to 10. But let's look at the function from 4 to 6. We just said it's continuous on 2 to 10, and so we can also say, therefore, f of x is also continuous on the closed interval from 4 to 6. And those are the values I'm going to use for my next part, because remember, I have to say that f of 4 is equal to 1, and f of 6 is equal to 4. I need to pick values that 3, this value I'm trying to confirm is inside, is in between these. I have to actually kind of sandwich it in there. So I'm going to pick 1 and 4 as my function values because 3 is in between them. And now let's articulate our argument here. So since f of x is continuous on the closed interval from 4 to 6. And so I do have to pick that 4 to 6 interval where I'm using this to kind of work and surround 3, if you will. So since it's continuous on 4 to 6, and because, and this is where I'm going to build my statement that f of 4 is equal to 1, which is less than or equal to. Again, the value I'm trying to show is that it goes through 3, which is less than or equal to 4, which equals f of 6. So I have said it's continuous on 4 to 6, and 3 is in between f of 4 and f of 6. Then there exists a value on the closed interval from 4 to 6 such that f of x is equal to 3 by the intermediate value theorem. And again, when using this theorem, you do need to cite it, and you can abbreviate it. But there's your airtight argument, that there exists an f of x equal to 3 somewhere on the interval from 4 to 6. It did technically ask us to show that it exists on the interval from 2 to 10. We actually gave it a more narrow answer there, but we can say that it logically follows that if there's a value on 4 to 6, that means there's definitely a value on the interval 2 to 10 such that f of x is equal to 3. And that's just me making sure that we answered what it actually asked us to. And it's logically follows. We said, hey, there's somewhere it's 3 between 4 and 6. That means it definitely is also 3 between 2 and 10. So make sure that you look at this and say, you have to pick an interval that actually surrounds the value you were looking for. We needed to show 3, so we could not just pick the endpoints. We had to actually go find an interval that surrounded 3. The other thing that's true about this particular question here is you actually could have shown that it equals f of x, that f of x is equal to 3 twice. You could have said what we just did, that somewhere between 4 and 6 it equals 3. But you also could have said that somewhere between 6 and 8 it equals 3, and that would give you 2 instances where f of x is equal to 3. So you actually could have verified on 2 to 10 the existence of 2 values where f of x is equal to 3. But in this particular case, it only asked us for 1 instance where that was the case. We were able to show that it happened on 4 to 6.